Here's a demo of the sampling distribution of the mean and the central limit theorem. On the left here, I've got my master collection. I've got a population, and it's done by a census, literally the United States Census, of a bunch of people in Florida. So it's a very large number. It's 5,000 people, and I'm just collecting their ages. So here's a histogram of that data. That's the population. And here's the mean age. It turns out to be 35 and a half, basically. And what we'd like to do is we'd like to find out what happens if we took a sample of 100 people out of that. What's the mean likely to, how does the mean of that sample behave? And what we're working up to is the situation where we don't know this data. And somebody just does the sample and tells us the mean and then says, how accurate do you think this is? How close is it to this number, which we're not going to know in reality? So in order to figure that out, first we've got to look at the situation where we do know this in detail, and we do know the actual mean of the population. And then what we're going to do is we're going to look at a bunch of hypothetical samples and look at how much they vary. And the claim is that we're going to just see a normal distribution pop out, seemingly out of nowhere, which is the central limit theorem. So here's what we do. We've got a sample. Here's one particular sample out of the 5,000, 100. Notice that that's less than 10% of the 5,000, but it's a fairly large sample. It's a decent sized sample, and we're hoping that the central limit theorem will apply. This is not a very symmetrical distribution. It's not super close to normal already, so we're going to need a pretty decent sample size, but it's not ridiculously bad. So hopefully 100 will be enough to see that come out. So here's one single sample and the distribution of ages in that sample. There's no reason why this would itself would be normal. This is the distribution of the sample, or of one particular sample. Don't confuse that with what we're going to talk about in a second, which is the sampling distribution of the mean. It's just one particular sample, and it's all the data, everybody, all the ages of all the people in it. That's not really what we're interested in right now. We're going to pull out one statistic, one summary measure of the data, namely the mean of all those guys. And we're going to see how that behaves across many possible samples. Because we want to get an idea of how the mean would vary from sample to sample in order to get an idea of how unpredictable it is and how inaccurate it may be as a measure of the reality. So here's what we're going to do. Let me open this up. This is measures from sample collection 1, and what I've got is the mean. I put that over in here, and I'm going to just collect, let's say, I'll collect 5 measures right now. So let's put that, oh yeah, this just got, I need to reopen this guy, that's fine, won't take but a minute. Here's the table, boom. Okay, so there's the mean age. Okay, so what this says is each row of this guy is actually a different version of these samples. This was just one example of a sample, but it's actually been rerun multiple times, and now it's up to 10 times. And we've got 10 versions of what the mean age would be across those samples. Notice they're all in the mid-30s. Well, this one's a little high. They're fairly close to 35.55, and I'm going to drag that down here. And so notice they're not terribly far from 35 and a half. But what distribution do they have? And what's the probability that they are pretty inaccurate? Well, like, what's the probability that it would be bigger than 38 or less than 32? How can we figure that out? Only if we know the distribution of this guy. So if we've only done 10 hypothetical samples, it doesn't give us a very good clue. Well, is there some underlying probability model going on here? So that's why we're going to do more samples. So let's go back to here and inspect it again. And let's collect 50. Let's not have the animation on because I hope that'll be faster. This can be really slow otherwise. Okay, here we go. So what it's doing is it's creating a bunch of different samples. You can see these histograms flash up there, or they were flashing for a minute there, of all the different the distributions of the individual samples. But remember, we're only taking the mean each time. It might seem wasteful, but remember, we only do this sort of hypothetically to get an idea, and then we prove a theorem, and then we never have to do it again. This is what we really care about, is for each of those different samples, we've calculated the means, and those guys are all clustering around 35. Notice, ooh, here's one that's 40. That's particularly high. There's ones that are about 30 to 31. That's kind of low. But we can see that they are clustered right around 35 and a half, pretty much, and they're not incredibly spread out. And now let's go ahead and collect. Let's see if we can take enough time to collect 100 more. It's collecting all the samples. It's got all kinds of different funky histograms flashing up in the middle there. They don't necessarily look like this or like a normal distribution. But then each time we calculate a sample and we calculate the mean, we're filling in the sampling distribution of the mean. This is starting to look plausible that it might be given by a normal model. You can see it's still peaking right around 35.5. It's not super spread out. And remember, the measure of how much we expect this to be spread depends on the sample size. The n is 100 for our sample, and so root n is 10, so we're going to be taking whatever the standard deviation of the population is and dividing it by 10 to get an idea of what we'd expect for the standard deviation here. This is looking definitely different from this, which is okay, and more like a normal model. Let's do it one more time. To really be convincing, we might have to do maybe 1,000, I don't think, and this is a slow program. It's not meant for speed, it's meant for kind of displaying what it does. But as you can see, it's still something that's peaked in the middle, it's nice and unimodal, it's pretty symmetric. And so this is the normal model appearing as the prediction of how variable the means of all these samples are going to be. And why is this so useful? It says that suppose I didn't show you this picture and I just gave you one of these numbers for the mean age up here, and I just gave you the number 36.37. The point is that if I just picked one of these at random, it's very unlikely that I'm going to pick one of the numbers that's very far from 35.5. I maybe could pick something 40 to 41, 30 to 31, but it's unlikely. If I look at all these dots, picking one of these dots basically says which random sample that I take. And most of them give a pretty accurate answer for the age. More than that, we can predict, if we believe this is really given by a normal model, we can predict what's the probability that they're more than a certain amount away from reality. And that's the basis of confidence intervals and hypothesis testing, which are our next subjects.